So last time we looked at how to calculate the moment, and also we know how to calculate the axial force on the column. Then the next question is how to find the reinforcement in the column, the reinforcement in the wall. How to find the reinforcement in the wall? So these are walls that may be about say 6 meters long, right? So what you do is there are two ways of finding the reinforcement. If there is no significant out of plane moment, then we can consider this as a column. And then say, you know, the corner 0.5 meters is going to be, oh, say 0.6 meters. Corner 0.6 meters, we'll have a concentration of reinforcement as in a column. And this is going to behave as a column. So if it is behaving as a column, there are different interaction charts. So if you are using the interaction charts given in BS code, we have to find N more BH squared. Also, we have to find N more BH. And then say this value is 1.5. This value is 12. Then we will be able to make use of a chart like this. Say here we are using grade 30 concrete. The reinforcement strength is for 1/60, and DOH ratio, that is D is the distance to the center of the reinforcement. So let's say DOH ratio is something like 0.9. Then if MOBH squared ratio is 1.5, somewhere here, the NOBH value is 12, then you can straight away find the amount of reinforcement to be provided. In those, so you can straight away find the amount of reinforcement to be provided, which is about 0.4. So then we can work out the other details. So let's do a proper example so that you will be able to understand it better. So stop share. Right. So let's take an example, and if you look at the wall that we designed last time, so moment is about so we got moment values in the range of 12,000. Let's take an example where we have a wall carrying an axial load N of say 22,500 kilonewtons and a moment of, let's say, 5,000 kilonewton meters. see whether this 5000 is enough to show the divided by 250 divided by 6. Let's say the moment is 10,000. Right. So we have a moment of 10,000, axial load of 22,500 kilonewtons on a shear wall, on a concrete wall, having a thickness of 250 millimeters. The length is 6,000 millimeters. The question is, how do you find the reinforcement in this wall? We know the moment, we know the axial force. So one of the options available is, we can say that so we can say we are going to provide a concentration of reinforcement over a length of, let's say, 1 meter. So at each end, we are going to get a concentration of reinforcement over a length of 1 meter. And then we can find the distance to the centroid, that is D, is equal to 6,000 minus 0.5, so 5 minus 500, and this will be 5,500 millimeters. Then you can find the DOH ratio, 5,500 divided by 6,000, and you will get up with 0.916, right? So what you can do is, we can find the N over BH value and M over BH squared. N is 22,500 to 10 to the power 3 divided by 250 multiplied by 6,000. So we get a value of 15, and the bending moment is 10,000 into 10 to the power 6 divided by 215 to 6,000 squared, and we'll get 10,000 by 250 divided by 6. We get 1.11. So what you can do is, let's say we are using grade 30 concrete. So what you can do is, I'll share the screen and show you. So here you can see FCU is 30, and here we are using 460 strength reinforcement. D over H ratio is 0.916, so I'll use 0.9 chart. And then this value is 15, and MOBH square ratio is 1.11, so somewhere here. And you can see we need about 1% reinforcement. So 100 AS over BH is 1%. So stop share, then you can see the sheet. So it's 1%, which means AS is equal to 100. B 6,000. Sorry, 250 multiplied by 6,000 multiplied by 1 divided by 100. So you can see 250 multiplied by 6,000 divided by 100. So we need 15,000 square millimeters of reinforcement. So what you do is 15,000 square millimeters divided by 490. So you can see we'll need about 32 bars. We need about 30.6 bars, which means we can provide 32 bars of 25 millimeter diameter. So what we can do is we can provide 8 bars, 2, 4, 6, 8 bars over a length of 1 meter. This side also another 8 bars. And we'll repeat the same thing on the other end. And the important point is all this reinforcement should be confined. So we'll have additional links to restrain the bars like that. And then what are you going to provide in this area, which is having a length of 4 meters? In that area, you will provide the minimum reinforcement. So you provide the minimum reinforcement in this area. So what is the minimum reinforcement specified? There's a difference between Euro code and the British code. British code, generally we go for a minimum of 0.4%. And in the case of Euro code, you can even go up to 0.2%. So, but if you look at the way that we practice in Sri Lanka, still, we prefer to go for this minimum of 0.4%. So now the reinforcement at the ends. Here we know the reinforcement. Here we know the reinforcement. And in this area, that is the center 4 meters, we have to provide 0.4%. And here we are considering 1 meter length. So S is equal to 0.4 into 250 into 1000 divided by 100. So we get 0.4 into 250 into 1000 square millimeters per meter. We get 1000 square millimeters per meter. So which means we can use T16 at 200 center to center. So in these areas, we'll have T16 bars at 200 center to center. And these areas, we'll have T25 over 8 bars in each phase. So we can arrange the reinforcement like this. And in the horizontal direction, generally we provide 0.25% reinforcement. 0.25 means, when you add the reinforcement on both faces, you should end up with 0.25. So that is one way of actually providing reinforcement when the moments are known. So when the moments are known, moments and the axial forces are known, that is one way of actually providing the reinforcement. Is it clear to you?
Excuse me, sir.
Yeah.
Sir, you have taken the confinement length as 1 meter from each side, right? So is there any rule to take?
No. There's no hard and fast rule. But generally, when you are taking this confinement length, you have to take a reasonable distance. So you can see for this 1 meter, this DOH ratio remains around 0.91, right?
Yes.
Because, when I am providing 8 numbers of 25 millimeter bars, I need a reasonable length. Say, when you are providing 25 millimeter bars, 1000 millimeters divided by 8 bars means the bar spacing will become 125 millimeters, right? So
Yes,
if
sir.
you want, you can even go for something like 0.6 meters and concentrate it. But trying to concentrate too much means, there will be a lot of congestion of reinforcement at the ends of the wall. So that's why, we go for a reasonable length like 1 meter for a 6 meter wall. But anything between 0.6 meters to 1 meter will be okay. But if you go for anything less than 0.6 meters, you will find that, the distance between bars will be reduced significantly. Then you will find that, when it comes to concreting and so on, there can be difficulties. Is that clear?
Yes, sir.
So you have to get a reasonable value, not a very high value like 2 meters. You will not go for 2 meters, but anything between 0.6 meters to 1 meter would be reasonable for a wall of 6 meter length. So if the wall length is 4 meters, you will definitely go for something like 0.5 meters, right?
Okay, sir.
It's
Thank you.
clear. Any
Yes, sir.
other question like that? Is, uh,
Uh,
is it
Excuse me,
clear
sir.
that how we find the reinforcement?
Sir,
Yeah.
sir, while finding the t value, how did you subtract that 500 from
Yeah,
6,000?
actually, I considered that the end zone will be 1 meter.
Yes,
So
sir.
the midpoint of end zone is 500 millimeters from the is 500 millimeters from the end of the wall. When I say 1 meter,
Like a midpoint of the reinforcement?
yeah. So because all these reinforcement will have a centroid. So I
Yes,
have to
sir.
consider this. I have considered the centroidal location of the reinforcement. Okay.
Okay, sir. Understood, sir. Thank you, sir.
Anything else? So this is one way of finding the reinforcement in the concrete wall. And then there's another way of finding the reinforcement in the concrete wall, because in our calculations last time, if you look at the calculations, we found the stress distribution. We actually found the stressors in the wall, right? And we found something like 10,000 kilonewtons per meter squared. Is that right? So let's say we have a wall, again 6 meters of length, and let's say the stress distribution that we finally get would be like this, and we get a maximum stress of about say 12,000 kilonewtons per meter squared. We get a maximum stress of about 12,000 kilonewtons per meter squared. And you can see it's a reasonable value, because when we did the calculation last time, we have found that some of the stresses can be 10,000 and so on. So if we consider a stress of 12,000, it would be a reasonable value. Is that clear? So on the other side, you might get something like 8,000. But that value is not important, because what happens is the wind forces can reverse. So if you get 12,000 here, you can get 12,000 on this side also. Right? So this minimum stress will be significant if you get tension here. But if you are getting compression, the minimum value is not very significant. But if you are going to get tension on this side, then the minimum value will be important. So you can see if we get something like 12,000, then there's another way of finding the reinforcement. And this is applicable if the whole wall is in compression. Whole wall is in compression, like this case. Throughout the wall, it's in compression. So what we do is we consider 1 meter length here, and consider that the stress is 12,000 kilonewtons per meter squared. And then what you are going to do is we consider this as a column, but you know, when you have a column, when you have a wall, I'm looking at an elevation of a wall. We have slabs supported by the wall. So these are slabs. So there's a possibility that, you know, there is a possibility, not always, that, you know, there can be some out of these loads might act with an eccentricity. So there might be a chance for some out of balance moment, So, or out of plane moment. So all this stress distribution we have obtained by considering in plane moments. But if they can be out of plane moments as well. So then what we do is, now if it is 12,000 kilonewtons per meter squared, then the equivalent load, the width of the wall is 250 millimeters. Then we are considering load over 1 meter is equal to 12,000 multiplied by 0.25. So you get a load of 3,000 kilonewtons acting over 1 meter. The load of 3,000 kilonewtons over 1 meter. So what we do is, we consider that this load acts with the eccentricity of 20 millimeter, and then we find the corresponding moment M, and this will give a moment of 3000 multiplied by 0.02, and you get a moment of 60 kilonewton meters. So what we do is, we consider 1 meter length of the wall, then consider that, you know, this stress can act at an eccentricity, and then find the corresponding moment. And then what we do is, we find NOBH, MOBH squared. NOBH is the stress, that is 12,000 or 12. When you are going to use the chart, you have to get the units in newtons per millimeter squared. So it will be 12. So 12,000 kilonewtons per meter squared is equal to 12,000 kilonewtons per meter squared is equal to 12 newtons per millimeter squared. And here MOBH squared is out of plane moment, 60 into 10 to the power 6 divided by 1000 by 250 squared. So that is the width of the wall. So you get 60 divided by 250 squared. That's 0.96. Then what we do is, we'll go to the column chart again. And then we have 12 here and 0.96. 0.96 is somewhere here. So we'll end up with something like 0.4% reinforcement, right? We'll end up with something like 0.4% reinforcement. So we say 100 AS over BH is equal to 0.4%. And then what we do is, we find AS, which is equal to 1000 millimeter squared per meter. So which means we'll provide 16 millimeter bars at 16 at 200 center to center. So we can provide 16 at 200 center to center. And then if you want to optimize, you can consider the next 1 meter. And if the stresses are significantly low, then you might end up with slightly lower reinforcement for the next 1 meter. But on the other hand, what happens is in these walls, always the stresses will reverse. So because of that reason, and also because the shear wall, the axial load also dominates. So you'll find unless the moments are very large, these reinforcement cannot be reduced. But in certain situations, if the variation is high, then you will find that, by using this method, every 1 meter, you can have a different reinforcement. So that's the other way of actually finding the reinforcement. So one is if you know the overall moment and the axial load, you can consider that the wall behaves like a column, and you are also sure that the out of plane moments are small. Then you can design it as a column subjected to single axis bending. So on the other hand, if you know the stress distribution in the wall and the whole wall is in compression, then you can design by considering 1 meter length at a time, and then you can determine the reinforcement. So there are two different methods of finding the reinforcement, and I have used the BS 8110 column design chart, but for Eurocodes also you get column design charts where the equation is slightly different, because what we find is NOBH FCU, FCK, something like that. So basically the method is the same, and if you know the overall moment and the axial load, you can find the reinforcement, considering it as a column. On the other hand, if you know the stress distribution, again you can find the reinforcement by considering 1 meter length of the wall. 1 meter length of the wall. Is that clear? So there are two different ways of finding the reinforcement. Any question on the second method? In the second method, we have allowed for any out of balance, out of plane moment as well. Because if you consider shear wall is very strong on its own plane, but out of plane, it is not very strong. It's weak. So we have to allow for both effects. Any questions on that? Yeah.
So if tension occurs in that one side, what we have to do?
Yeah, if tension occurs, now that means the wall will be cracked. Is that right? If tension occurs, we'll have a problem, because if tension occurs in the wall, now that tension will be transferred onto the foundation. And what will happen to now generally the pipes are designed to carry axial load, vertical load, or the compressive load. Is that right? But if tension can occur under the shear wall, then it's not a very healthy situation. So you might have to consider changing the configuration of the shear walls slightly, or you may have to consider transferring more load onto the shear wall, or you may have to do something. Generally, we don't like shear walls going into tension. The reason is, if there's tension in the shear wall, then that tension will be transferred to the foundation, and foundation will go into tension. Is that clear? So if there's tension, we don't like it. So that's why, you know, these coupled shear walls are so important, because once you couple the shear walls, the bending moments will reduce and the chances of tension occurring under the foundation can be reduced to a significant level. So basically you can ensure that no tension occurs under the foundation. Is that clear? We don't like tension in the foundation, no tension in the shear wall. That's why, you know, we have to make sure that reasonable load is transferred onto the shear wall, reasonable vertical load. So we don't like a shear wall that is not supporting any slabs, because if the shear wall is supporting slabs, then at each floor level, the slabs can transfer a certain amount of load onto the shear wall, and that will stabilize the shear wall. Is that clear?
Yes, sir. In
Yeah.
this method, we are governing that the tension will occur, but in the other method, we not governing that tension will occur and
So when you are
considering.
using the column interaction chart, it is automatically taken into account. In the column interaction chart, if tension occurs, that is automatically taken into account, right? Because the column interaction chart, there are two. So if you are somewhere here, then your design is governed by the compression. That means the whole section is in compression. But if you are somewhere here, then the section can be in tension as well. But you know that, you know, in a column or a wall, we like to be in this region. Why? The whole section will be in compression. We like to be in this region. We don't like to be in this region. This region, the axial loads are so low, bending moments are high, so tension is occurring. Whereas if you are in this region, then the axial loads are high, bending moments are low, then the whole section will be in compression. Is that clear?
Yes, sir. Thank you.
So if you are using, if you are having a shear wall, make sure the shear wall is loaded. Otherwise, you know, the behavior of the shear wall may have problems, because, you know, when you are designing the foundation, generally we design the foundations for loads acting downwards, not for the loads acting upwards. And if the loads are acting upwards, the pile can uproot. So that we don't like very much. Okay. Is it clear?
Yes, sir.
So if you want, you know, you can go to consider the fundamentals and design a wall as a cracked wall. That is also possible. But then the design becomes difficult. But, you know, the general situation is anyway, any tension in the shear wall is not desirable. So because of that reason, we have to make sure the shear walls are loaded by a reasonable, to a reasonable extent. Okay. So if you have a very lightly loaded shear wall subjected to very high bending moment, you can design the wall, but, you know, design the foundation will be a problem. I hope that has clarified the situation. Okay. Any other question like that?
Excuse me, sir.
Yeah.
So in the first method, the n value should be, we need to calculate that, no?
No,
Using the
actually,
low.
in the couple shear walls, can you remember last time we calculated the axial load?
Yes, sir. That is due to the moment, right? I mean, due to the lateral load.
No, due to lateral load, you get axial load. But in addition to that, you get axial load due to the self-weight.
Yes, sir. That's what I'm asking. We need to combine those two.
Yeah, you have to
For this
combine
one?
all that and get the final n value on the wall. And
Okay.
also you have to get the m value on the wall. N
Okay,
value
sir.
and m value, right? And if
Okay,
you
sir.
know those two, then you can find the reinforcement by using that particular method.
Okay.
Right? On the other hand, if you know the stressors, you can use the second method.
Okay, sir. Okay.
Any other question like that? Okay, then share this. I'll share the can you see this? Can you see this on design modeling of tall buildings for structural analysis?
Yes, sir.
Yeah, okay, good. So basically, now when you are doing the analysis, you will do the analysis in two different levels. The first one is the preliminary analysis. Preliminary analysis. So the idea of preliminary analysis is to get some idea about the deflection of the structure and the loads acting on structural elements and so on. So when you are conducting preliminary analysis, there's only one or two things that I want to show. It is actually, if you want to get some idea about the moments on shear walls and so on, then you can replace all the shear walls by using columns where the column I value will be the column. What you do is you define a column and then you can modify the I value. You can assign a high I value to the column to represent the wall. So basically, you can rather than modeling the wall, if you want, you can model a column, and so when you are modeling the column, so you can select a small column size, but you will get EH. So you will get the I value about this axis, that is 112 B H cubed, and in most of the programs you get something called set modifiers. So basically you can modify the section properties of elements. So you can allocate a small column, but you will go to set modifiers and increase the I value so that it will match the I value of the wall. So basically when you are doing analysis, if you want, you can actually represent the walls as columns and then perform the analysis. So that is one of the things I wanted to show you. And also sometimes you get shear walls like this. So in such situations, what you do is, here the centroid of the axis is changing. Sometimes you ignore it, but if you want to take that into account, then what you need is you need something called a rigid arm here. So you will have a horizontal beam connecting the other shear wall at the upper level, and for this arm you will allocate a very high I value so that the deformation of the arm and the wall, this column or the wall, here you will get a perfect 90-degree angle, and so that way you can accurately model the wall by using columns. So that's another thing that you can just use. So when you are modeling couple shear walls, you can make use of this method. So I'll show you. So if you want to model a coupled shear wall, so coupled shear wall will have the walls and the beams. So if you want, you can say there is a column here, there's another column here, and it has a rigid arm level. And then your model will be something like this. The two columns at the center of the wall, then you will have rigid arms to represent the width of the wall. And then you have the actual connecting beam connecting the rigid arms. So you can see why we need this particular method of rigid arms, and that is to represent the actual dimension of the column. Because when you define a wall as a column, we cannot represent the length of the wall. So if you want to represent the length of the wall, how we do that is by defining a rigid arm. So the important property of rigid arm is I value of the rigid arm. We use a reasonable section and then we multiply it by 1000 times I beam. So you define a beam section, then what you do is we will go to set modifiers and we multiply the section property or the I value by 1000, so that it will behave like a rigid arm. So the idea of rigid arm is that this arm is not going to deform, it is rigid. So you get 90 degree before the deformation and 90 degree after the deformation, and over the length there's no deformation in the arm. So this way you can actually, if you want, you can represent the walls as columns and then you can combine them with rigid arms. So these are some of the modeling techniques. Sometimes you find that these are useful, but to a lesser degree these days, because when you look at most of the programs, you can see we have shell elements and we can easily model a shear wall with its actual size. Then the other thing that I want to highlight is that sometimes we get slabs instead of beam slab construction. Sometimes we get flat slabs. So when you get flat slabs, for the vertical load analysis, what we generally do is we represent we consider that from one center line to the other center line, this slab will act like a beam and then transfer all the loads onto these columns. So that's how we generally consider. But when it comes to lateral load analysis, sometimes it's not good to consider the full width of the panel as effective. So what we do is we have to find the width that would be effective in resisting the lateral loads. So when you are doing the analysis, if you want to represent these slabs as beams, then we have to find the width of the beam, and to find the width of the beam we have to consider the size of the column, the distance between centers of columns this way and distance between centers of columns this way, and then based on that we can find a width that is effective in resisting the lateral loads. And how do you find that is by considering these ratios. U over A ratio, U is the size of the column, A is the distance between center lines. So you have to find U over A ratio. And then we also find B over A ratio, B over A ratio. So you have to find U over A ratio and B over A ratio. And from that you can find B dash over B ratio. And that will give the width of the slab that you have to consider for modeling when you are modeling for the lateral load analysis. So when you have flat slabs, you may have to consider a reasonable width of the slab as the one that is effective in carrying lateral loads. And if you want to be a little accurate, then you can use this method. The other method is you will consider half the width, half the distance between this will be equal to the slab that will be effective in carrying lateral load. So basically we say B dash is equal to B by 2 when you are designing, when you are analyzing the structure for lateral loads. So this actually comes only in the case of structures having flat slabs. But in normal beam slab construction, we don't get this type of problems because connecting the columns, we'll get beams. So we'll be directly representing the beams. But so when it comes to detailed analysis, generally, you know, when you are doing the analysis, we ignore certain effects. The effects that are not very significant, we generally ignore. For example, when you are designing a beam, if you have a beam, you know, subjected to vertical load, it will bend downwards. It will bend downwards. So that's the normal behavior we expect. But in a three-dimensional structure, there is a possibility for beam to deform in the other direction. So for example, when you have a beam subjected to vertical loads, we expect it to bend like this. But if you look from the plan view, then there's a chance that the beam might, when you look at from the plan view, the beam might deform like this also. But in three-dimensional analysis, we ignore all those different effects and we consider the beam. What is important is only this. And similarly, last time I showed you, generally when we have a beam subjected to vertical loads, we expect it to carry only the bending moment. But I also showed you some situations that can happen when the beams are having heavy loads transferred at an eccentricity, where the beam can be subjected to a torsional moment as well. Where the beam can be subjected to a torsional moment as well. So there can be situations like this, but these are exceptional situations. But normal situations, we consider beams to carry the vertical loads and deform vertically, so that the important behavior that we have to capture is the bending of the beam, nothing else. Because when you are doing the three-dimensional analysis, when you consider a beam element, you get 6 degrees of freedom. You get a shear force, moment, and axial force. And here also you get the same things. So you get 6 degrees of freedom. Then when you are doing the 3D modeling, we have to be aware of the important aspects that we are looking for. So the important aspects that we are looking for will be the main actions. So for example, for beams, what is important is the bending that occur due to vertical loads. And similarly, for many other elements, For example, for slabs, we don't consider the deformation of the slab in its own plane, but we consider the deformation of the slab out of plane. So what is important for us is out of plane deformation of the slab due to the vertical loads, and we generally ignore the in plane deformation of the slab. And actually what we do is we say the slab behaves like a rigid diaphragm, and there's no deformation of the slab in its own plane. So which means the deformation of all the members due to the in the building will take place like this. That means when the building is rotating, the whole building will rotate by the same amount. So that's a type of behavior that you get with rigid diaphragm behavior. So basically, when you are doing 3D modeling of a building, you have to keep in mind is every element will have so many degrees of freedom, but out of all this, for our design purposes, we use only the most important or dominating behaviors. We use only the most important or the dominating behaviors. So that's the summary of this note, and so you can I'll upload it. You can just go through it. It just gives some useful information that can be used by you when you are doing 3D modeling of structures. So that is the summary of this note, and I have given one example also how to find this width of the equivalent slab, but that is applicable only for flat slabs. But if you are modeling a structure with beam slab construction, then you get mainly the columns, beams, and slabs. If you want, you can represent the slabs. On the other hand, you can say the flow is acting with a rigid diaphragm, and then you can even if you don't model the slabs, still the program will assume that there is a slab and the behavior is rigid diaphragm. So those are the important things you have to keep in mind when you are doing 3-dimensional modeling. So if the time permits, today we'll see whether we can have a small, brief session using SAP 2000. But before that, when you look at tall building, all these buildings are subjected to lateral loads, and we have already done one example by using couple shear walls. And one of the problems that occur in tall buildings are that they are all cantilevers almost fixed at the ground level. So when you have a cantilever, then the cantilever will deform when it is subjected to lateral loads. So all the tall buildings will behave with certain deformations, and then in a day with heavy wind, you will find that the building can move as well. And when there is a movement in the building, you will get some accelerations associated with it. So you have to actually control those accelerations, and that's what we are going to look at after the lunch break. So if you do you have any question on these minor things that we discussed now, like representing the wall as a column, and then to represent the actual dimension of the wall, how to use the rigid arms, and also the importance of considering only the important effects when you are doing the modeling. Any questions you like to ask? So in that case, after the lunch break, you have to use the second link. You have to use the second link and join. And what I do is we'll discuss how to calculate the wind-induced acceleration of buildings using the Australian code. Okay. Shall we break for lunch?
Okay, sir.
Okay, right. Okay, thanks.
Thank you.